this time I'm not going to talk about the wheel of Scalar fortune, but about monad transformers. So I wonder whether any one of you knows that feeling when you go to a conference, you hear this talk about this fancy new technology, you almost seem to understand what it does, you're very excited, but then after a week or two, you try to explain this technology to someone, and then actually you realize that you don't understand how it works. And the moment of enlightenment only comes when you need to solve some kind of problem that seems totally unrelated to what you heard during this talk. But then after trying to solve this problem, you notice that there are some regularities and probably someone must have already solved this before. So this was actually my story with understanding monad transformers and also some other concepts from functional programming. And I want to share the story today. So let's jump to the example I prepared for you. So let's say that we have some simple API. We have our service, it's called from scratch because we'll be learning from scratch here. And we want to find some company by some user ID. The user and the company are parts of our domain model. They have some simple properties. And we have some private methods that normally probably would be dependencies to our data access object or repository or whatever you'd like to call it. And they are returning a user by an ID and a company by user. So in this very simple scenario where the method that finds a user just returns a user and the method that finds the company just returns the company, implementing our API method is fairly simple because we just need to say find company by user, then inside we say find user by ID, and that's it. So that's how you implement it. Now we can switch to the QA session, but not yet. So in real life, in our real world scenarios, this is very seldom that simple. So usually our repositories or the objects that we use to access our data handle some kind of various situations about whether the data exists or not, or how the computation is performed. So to start very simple, for example, we can assume that in a real world, the ID provided here may not be an ID of an existing user, so the user might not exist. Then our dependency, which fetches the user, wouldn't directly return a user, but it would return an option of a user. The same can happen to the company repository. The company may not also exist for the given user, so here instead of company, we'll have an option of company. And now we see that our API implementation doesn't compile, which is understandable because the types are different. Actually, with options, we are able to solve it pretty easily by actually just reverting the order of the methods here. So we'll start by finding the user by ID. We provide the ID. We use the flat map combinator on the option that was returned, so we can provide another option here. And here we use the find company by user method, which takes the user and finds the company. Well, that return type has changed, so we're going to update it to the option of company. And this is also a very simple implementation. Actually, we can use some syntax sugar here, the for-comprehension, instead of doing the flat maps manually. So we can say that we are fetching the user by ID like this. Then we are fetching the company by the user like this. And then we return or yield the value of the company. So this is how we would do it. Well, this is a nice solution if our repositories only have the notion of the user or company existing or not. But what happens if we add some more real life to it and we say that those computations are asynchronous, so they are not returning the options immediately, but they're returning them in the future. So if they return them in the future, we actually want them to return not options, but future of options. So here the service would, or the repository would return a future of an option of a user. And here the company repository would return a future of an option of a company. So now we notice that our code doesn't compile anymore. There are some issues here. First of all, we are missing execution context. This is actually a nice feature of IntelliJ that is called show implicit hints. If I disabled it, you will see that there are only those ellipses underlined with a red line showing that something is wrong. But if I use the show implicit hints feature, the compiler or the IntelliJ would actually tell me what's missing here. So the execution context is needed here because we are doing a flat map on the future, and the map, since for comprehension, is just a syntax trigger for mapping and flat mapping. And if you want to do it on something on the future, like map or flat map over it, you need to have the thread pool that you are going to use for it, which is the execution context. So this one we can solve easily by just providing an implicit execution context here. Like that. And the bug here is fixed. So if you're not familiar with implicits, which is very powerful but also sometimes tricky feature of the Scala language, you can think of it in two ways, whichever is you find more suitable. So one way of thinking about implicits is that is providing some context to the computation that you are doing. So here we say that the find company by user ID is executed using some context that is available from somewhere, and this context here is the execution context. The other way to think about implicits is compile time dependency injection, because what we say here is nothing more that at compile time we require an execution context to be present somewhere. Where do we take it from? It depends. So it can be specified somehow in the execution points, but this is actually nothing more than the compile time dependency. So we solved the missing execution context, but now we can see another error here, which says that, well, our find company by user method requires a user, but what we actually provide here is an option of user, because what we do here, you are calling find user by ID, which, as you remember, returns a future of an option of a user. So if we do flat map on that, we are actually flat mapping on the future. So the value that we get is the option of user. But what we would like to be able to do here is when doing a flat map on the result of this method, so when calling flat map on the result of find user by ID, we wouldn't actually like to work on the future, so on the external wrapper, so to say, but rather on the internal wrapper, on the option, because we would like to directly have access to the user, not to the option of user. So let's try to see whether we can fix it ourselves and implement some kind of wrapper for our types that would let us do it. Since we would be manipulating the types of the methods here a bit, let's introduce a type alias for that. So this is easier to refactor. So here we can say that we'll have a type called, let's call it effect. So effect in our case is a description of something that is happening. So our effect here says that we are having an asynchronous computation that possibly returns a value. So this is a future of an option of A. And actually, we also need to change the type here to a future of option of company, because this is what is going to return. But here we are going to keep the type. So in these two cases, I'm going to replace the future of option with effect. So with our type alias effect here. But I'm doing it here because those are private methods, so they are not exposed as a part of our service. But here, since we are exposing a method publicly, we want to have a proper type return that is recognizable. This will become even more important if we start using types not from the standard library. So as a contract of our public API, we only want to return types from the Scala language. Okay, so let's now go back to the example and try to implement the wrapper for a new type for our effect. That would actually let us access the internal object. So inside the internal wrapper when doing map or flat map. We're going to call it, since this is an option inside the future, we will call it option inside future for readability. This is going to have a generic type parameter, and it's going to be a wrapper for a value, and the value that is going to store inside would be of type future of option of A. And now what we want to do is to be able to use our wrapper inside the for-comprehension. So as you may remember, for-comprehension is a syntax sugar for map and flat map. So in our wrapper, if we want it to be used in a for-comprehension, we need to provide the map and flat map methods and implement them. So we need a map method that takes another generic type parameter B, and it takes a function from A to B, and returns the option inside future of type B. And it has some implementation. Let's write it later. And similarly, we need a flat map. And the difference between map and flat map is that it is in the function that they take. The return type is the same, is the option inside future of B. But in flat map, we are taking a function that returns the wrapper. So for map, the function is from A, so from the original type to some new type, but the type of the value. But in flat map, the function is from the original type A to a wrapper of the new type, wrapping the new type B. So now let's try to implement it. So here, once again, what we want to achieve is to be able to call, when we are mapping over our wrapper, we actually don't want to call map on the future here, but we want to map on the option, so that in the map method, we provide a function that does something with the A thing that's inside an option. So we want to go twice inside the wrapper so that we get to the most internal one. So we're starting with the value, and we are calling a map on the value. So value is the future here. And when we are calling map on the value, we are actually manipulating the option. So now we want to do the actual transformation of the content of the option. So we take the option and map it with f, which means we apply the function that we have here to the option, not to the future. So this way we got to the very inside of our double wrapper and performed an operation, the map operation, on the value that's inside the option. So once again, this is where we operate on futures. So again, we need an execution context here, which is the thread pool for the future operations. And we also need to fix the return type, because here this returns a future of option of B, but we want to return our wrapper. So let's just wrap it with the option inside future. So this is the implementation of map. Similarly, we're going to write our implementation of flat map. So the intention here is the same. We don't want to flat map over the future, but rather on the option. So we want to get inside our container, inside our wrapper, and do the operation on the option. So we already know that we will need to wrap it into the option inside future. And we'll start similarly with calling value, this time flat map, because we are flat mapping over the value. So this is flat mapping over the future. So here, since we actually want to flat map over the content of the option, not the content over the future, we need to provide a function that takes the option and returns a future of the new type. So we would have two cases here. If the option contains some value of A, then we want to apply the function to that value and change the type here, because because here we don't expect our wrapper, the option inside future, but we expect F2 to return a future. So we are accessing the value that is inside our wrapper. And in case the option is empty, so there is nothing there, we want to return immediately completed with a value of none. So we actually need to wrap the value of none into a future. And for this, we are using the future successful method. Also, please note that using future successful is recommended here instead of using future apply like that, because future apply futures are eager in Scala. So this means that a new thread is started immediately when you call future apply. And if you just want to wrap a static value inside the future, you're actually using future successful for that. So once again, what we did here, we needed a wrapper for our future of option that would let us do mapping and flat mapping on the thing that is stored inside the option. So normally calling map or flat map on it would work on the future, but we want instead work to work on the options that are inside. And this is why we have written our own wrapper that maps over the future maps or flat maps instead, depending on where are we, either whether in flat map or flat map. So it for example, map calls map on the original value and then applies the function that we provided on the option, so on the thing that is inside. And now, if we go to our type alias for the effect and we changed our future of option here to the option inside future, you can see that it almost starts to compile. At least we don't have the error here that the user is of the wrong type, because here we are able to access the user, and the user that is taken from here is the user, not the option of the user. But here you can notice that we need to adjust the return type, because previously we discussed that in our API method we want to return the plain future, not any custom wrappers. So here we want to return a future of option of a company. But our for comprehension returns our wrapper. So to change it, we need to take our wrapper and call value on it. And this, by doing this, we inside the for comprehension we operate on our wrapper, but then we are calling .value to extract the actual value that it was wrapping, which is the future of option of A. And this is how we could solve it. So let's now do an experiment and see what would happen if we'd like to implement it for some different wrapper, the external one. So we are still having an option of A inside, but we want to change the wrapper that we are using outside. And now instead of a future, it is going to be a list. So let's do some copy pasting here. And now in this part, we want to change the future to a list. So you can see that it's going to be changed in a couple of places. And now, surprisingly or not, you can notice that we are almost done just by copy pasting and by changing the type from future to list. So in particular, please notice that the implementation of the map didn't change. So actually, if we only change the external wrapper, the logic for mapping over the thing that is inside an option doesn't change. This is still the same. So this is independent on the external wrapper. The only thing that changed is here in the flat map. So this part here, you may remember that this is the knowledge how to wrap the value of none into our external wrapper. So previously we were using future as the external wrapper, so we needed future successful to have the value of none wrapped in the future. And here, in case of a list, we are using list apply. And by that simple change, this was the only change that was needed if we wanted to change the external wrapper. So we went from a future wrapping an option to a list wrapping an option by only changing one thing, the knowledge how to wrap a value as a simple value into our external wrapper. And all the rest of the logic for mapping and for flat mapping didn't change. So this could lead us to a conclusion that maybe we can do even better. So maybe we can do it in an even more generic way that, for example, would be independent of the wrapper, the external wrapper that we are using. So we will be able, whether it would be a future, a list, or anything else that can hold something inside, perhaps we can have a generic implementation for that. So let's try it. I'm going to wrap those so they don't distract you. I'm going to paste the code for option inside future once again. and do another search and replace. But this time I'm going to replace the future with anything. The anything here is not to be confused with any or any val. So the Scala types is just some arbitrary type name. So the purpose is just to denote that that we are going to use anything as the external wrapper. So it could be an option, a future, it could be a list, it could be something else as well. So let's do the renaming. Well, okay, now there are some more compiler errors that we had previously, which was expected. First of all, well, so at the moment, we don't know whether we are working on futures or not. So the execution context is not needed. So I'm removing it for clarity. And here, the first problem is that we don't know what the anything type is. Well, this is understandable because previously we used some built-in types like future or list, but now we don't know what it is. So we would need to provide it as a generic type parameter here, like that. This still doesn't compile because you can see that we are using the anything type as a wrapper for something. So here in this type parameter, we need to denote that that anything type is a wrapper for something. So it would have another generic type. And we do this by defining something called a type with a hole. So this is a hole here, and we're basically saying that the type anything can wrap something, so or it even needs to wrap something. So you can provide any type here that would be able to hold something inside. So this could be a future, this could be a list, but this cannot be an int, for example, because int doesn't have a generic type. It's not a wrapper for anything, but futures or lists are. So we would be able to provide them here. The other things that we are missing, well, we need to fix the types here because now our option inside anything takes two type parameters for the anything and for the B. So let's do it like that. And now you can notice that we are actually missing the knowledge how to map and flat map over the value, because we just said that the value can be of type anything, so it can be any wrapper, but we don't have any information or any knowledge how to call map and flat map. So let's try to solve it in a naive way and create our own trait that would provide those methods like map and flat map and see if it can help us. So I'm going to create a trait called map and flat map with some generic type A, and it's going to contain those two methods. So it's going to contain map with another type B that takes a function from A to B and returns the mapped flat map of B. So this is map, and similarly, we'll create a flat map with the only difference being the return type of the function that we are supplying here. And now what we can try to do is try to say that this type, anything, needs to implement our map and flat map trait. So you can do it by providing a constraint for the type. And this needs a type parameter, let's call it some t, which also needs to be provided here, so that, so to say, it's propagated from the anything to the map and flat map, so that we know what the actual type is. Now you can see that it almost started compiling, so or at least it looks like it did. So first of all, here we are almost done. The only information that we are missing now is what we know from the previous example. So this is, we are lacking the knowledge how to wrap a simple value like none here into our external wrapper, so into anything. So it looks like we need to provide another method in our trait that will be capable of wrapping the value, a simple value, inside the map and flat map. I'm going to call it pure with a generic type A, and it takes a value of type A and returns the map and flat map of A. And by doing this, we will be able to call value pure here. Okay, and now you can see that, well, it doesn't compile. And the reason it doesn't compile, we can see the errors in SBT here. So the problem that we hit at the moment while trying to implement it like that is that, for example, in the map, we are expecting the type that we have inside our as the value, which is the anything of option of B. And actually, what we are getting is the map and flat map of option of B. So this is our trait. The other problem with flat map is similar. So this is where we pretty much hit the wall. We would be able to solve it by doing some compiler magic with the types that we provide here to this map and flat map trait. But this is outside of the scope of this talk. Especially that even if we did this magic here in this map and flat map trait, we would hit another wall, so to say, because we would get to a point where we would need the future, the built-in future. For example, if we wanted to use our trait here, like with option inside anything, with the future, and I like that, for example, this would require future, the built-in future here, to implement our map and flat map trait. And well, this is directly not possible because future is a built-in type and we cannot change the inheritance hierarchy of it. So we can't make future implement our type, our trait. In order to achieve a working result, we would need to do some more wrapping. And so we have one wrapper, we would have another wrapper. So this is, and the wrapper would need to provide the information how to do map and flat map on the future. So it looks like the approach we started to take here is not the best one. It would be doable, but this would require a lot of boilerplate. And actually, we want to be able to do it in an easier way. And actually, here to make it compile, at least in the IntelliJ compiler, we can do something like that, because none is of type none. And we want not a type none, but we want an option of a generic type. So instead of using none, we are using option of empty, which is generic, and it returns instead of returning a value of type none, it returns a value of type option of A. So, but here, even though it compiles in IntelliJ, we are still getting the same errors that we've seen previously in SBT. So this is like some problem with the IntelliJ presentation compiler that it just doesn't show it. So once again, we could solve this by doing some type magic here, but anyway, we would get to a point where we would need future or another built-in type to implement map and flat map, but this is not doable without providing some additional wrappers, and we don't want to provide any additional wrappers. So let's forget about this solution for a second. So I'm going to remove the map and flat map from here. I'm putting the type hole here, and let's try to implement it in some other way. So once again, as I described when I started implementing this option inside anything, we are missing the knowledge how to run map and flat map over our type anything, and we also lack the knowledge how to wrap a given value into anything. So the other approach that we are going to take will be using implicits. So here, I think it could be useful to think about implicits as the compile time dependency injection. So here we would say that we want to have a value, I will call it FA, that is going to be a functor. And functor is a construct, so to say, from functional programming. And functor describes a way how to execute a map operation on a given type. So this FA or funct, which is a shortcut for functor of anything, we are requiring this as a dependency so that we know how to execute a map on anything. And we assume that this information is going to be provided. This is not, this doesn't yet say how to do it, but this is a compile time dependency on the knowledge how to do it. So at some point when we are going to actually run it or call this method, there we would need to provide the knowledge how to run the map. So an actual instance of the functor. But here, this is just a dependency. We say that we require a way to know how to run map on anything. So here we are going to use the functor, and the functor has a map method. So the syntax here changes only slightly because we would need to, instead of calling value.map, we are calling fa.map on the value. And you can see if you look at the syntax of the map method in the functor, it has two parameter lists. First of all is the wrapper that we are operating on. So in our case, this is the anything, and the second one is the function. So the second part didn't change because we did it previously as well. But instead of calling value.map, we are calling fa.map over the value. And by doing this, once again, by requiring a compile time dependency that provides a knowledge how to map over anything, we are able to use it to do the actual mapping. Similarly, we're going to do it with the flat map. So here we're going to have another implicit parameter. I'm going to call it MA, and I'm going to explain later why. Well, you will see why such a name. So here we would need two types of knowledge. First one is how to do a flat map on anything, and the second one how to wrap some value into our anything. So starting with a flat map, we have a flat map trait. And by the way, the traits here, they come from cats. So the functor or the flat map here comes from cats. There are other libraries that can provide the instances as well. I'm using cats. I think it's one of the most popular. So here we are saying for now that we have the value MA, which gives us the knowledge how to do a flat map on our type anything. And this is a compile time dependency. So at some point when we are going to call the flat map method, we would need to provide the actual value for the dependency. So the actual instance of this flat map trait or type class, because this is what it's called for anything. And similarly, as we did for mapping, we do a change here. So instead of saying value.flatmap, we say ma.flatmap over the value. And here we provide the other function. So once again, looking at the syntax, we can see that there are two parameter lists. First, once again, is the wrapper, so the value of type anything in our case, and the second is the function. And once again, you see that the second part here didn't change. So we are leaving it intact compared to what we did previously. The only thing that we change is that instead calling value.flatmap, we call ma.flatmap over the value. So now we know how to flat map over anything, but we also need to know how to wrap a value into anything. And this is done using another type class or another dependency that we are going to use that is called Applicative. And Applicative says, or Applicative knows, an instance of Applicative knows how to like call apply or the pure method on any value. So in other words, it knows how to wrap a given value into our type, so into anything here. So here, instead of using value.pure, we are using ma.pure. So once again, here we provided two dependencies. First says how to flat map over anything, and the second one tells how to wrap a value into anything. And it turns out that there is another type and another type class that actually combines those two behaviors, and it's called a monad. That's why I put MA here, because this is going to be a monad of anything. So we can, instead of using flat map with applicative, we can use a monad, because monad is a flat map and it is an applicative. So now you can see that like all of this compiles, and we can check it in SBT. It doesn't compile yet. Yeah, it doesn't compile. I was too fast, and I'm going to explain it shortly. So actually, let's use the implicit hints from IntelliJ once again. Yeah, well, it doesn't compile. I almost already explained it, because here we specified the compile time dependencies for a functor and for a monad, but I told you that we would need the actual instances for that, and now we didn't provide them. So here we are calling find user by ID, find component by user, and the arrows here mean that we are calling map and flat map over our wrapper, but we actually didn't specify how to flat map and call pure on a future, and we didn't say how to map over the future. So we need that knowledge from somewhere. And for that, we need to import the instances of those type classes, of the monad type class and of the functor type class. And the type class instances are provided by cats. You can find them, if we are talking about future, you can find them under cats instances future. So those are the implicit instances for monad of future and for functor of future. Let's see the compiler once again. Yeah, now the compiler is happy. Here you can see that we're already using our new wrapper as the effect type because we changed it previously. And now actually we can do it even nicer here in the implementation, because it turns out that, well, we already know that monad is a flat map and it is an applicative, but monad is also a functor. So instead of having a separate functor here, we could have a dependency, and instead of having the dependencies for each of our methods separately, we could have a dependency here on the level of our class. And actually, then we don't need the functor here, because since monad is a functor as well, we can use the MA here. So this is, once again, this is because a monad, apart from being a flat map and being an applicative, it's also a functor. So so we move the dependency, the compile time dependency expressed by implicits, from our methods, from map and flat map, to our class. And now you can see that this became unused, and this is because we are not calling flat map on it yet. And here the dependency is on the apply method, and we didn't yet create an instance of our class. So actually, the implicits here would only, the monad of future would be only needed when we create an instance. So this is the difference in the approaches. And now what we created here, once again, by specifying some dependencies, how to do map on an arbitrary value, how to do flat map on an arbitrary value, and how to call pure, which means wrapping our value into our class, anything in this case. So we invented a monad transformer, actually, because the type we implemented here, the option inside anything, it exists in cats, and it's called OptionT. So we can just substitute our option inside anything with option of T, and we are achieving exactly the same behavior. So that's why we do that's what we did. And that's what a monad transformer actually is. So this is a kind of a wrapper that lets you access if you have like two effects that are contained one in the other. Like in our case, it was an option inside the future, or actually an option inside anything. So for option inside anything, we can use the option T, so the option transformer, monad transformer. There are instances of monad transformers also for other types, like either, for example. But you can see that I hope that you see that there is really no magic inside. So to implement or to arrive at this solution ourselves, we basically needed to know. We started by needing to be able to map and flat map over the very inside value, and then we created the implementation requiring some compile time dependencies that would tell us how to do it. So this is how we invented OptionT. And now there's one more thing that I want to show you, because I got into this error once, and I was a bit confused because I didn't know what's happening. So let's say that we have a test method, and it uses the OptionT, so the monad transformer for option, and it uses a helper method called from option with a future. So this means that we are actually going to create a future of option of something inside, and we are providing a value of none here. So this is, as you can see, this is building an option of T with future, and well, the type is nothing. But the problem I wanted to show you is with the compiler error here. So it says that we need an applicative for future, but actually we imported all the type class instances for future here. So if we go for here and go to the future instances, we can see that, well, there is a monad of future here. And previously we learned that monad is an applicative. So if we have imported the monad for future, why does it complain that we didn't provide an applicative for future, since monad is an applicative? Well, it turns out if we go back once again to the future instances, that they require an execution context, and this is the actual problem. The reason for that, why an execution context is required, is that actually when you want to do a flat map on a future here, for example, well, flat map, since the futures are eager, requires an execution context. It requires a thread pool. And this is why an execution context is required to be able to import those, to use those dependencies. So here, in this case, when we are calling map and flat map, we already have the execution context here. So it was working fine. But here, if when we are on the class level, we actually don't have the execution context, but the compiler error is a bit misleading, because I would expect a message that, hey, you're missing an execution context, but it actually tells me that I'm missing an applicative of future, but I provided it. But we can see that we can solve it by providing the global execution context, for example, just for the sake of making the compiler happy. And now you can see that although it complained that it wants an applicative for future, it actually wanted the execution context for future. Okay, so this is it for the live coding. Actually, well, this approach may seem nice, but as probably every approach, every technology, it has some limitations. Well, first of all, if you care about performance a lot, you probably noticed that every map and flat map operation here requires an allocation. So we are creating a new object. So if your application is performance critical, you should really be careful with it, and probably you should do some performance testing to check whether you are not affecting performance too much with that allocations. Another thing that I already mentioned and that you need to keep in mind is that now you can see that here the type here that we are using for the effect is an option of T, so we are using it for the private methods here as well. But this comes from cats, so from an external library. And now if you are designing a library that you want other people to use, it's a good practice not to expose APIs, your API, in terms of the built-in Scala types. That's why I insisted on keeping a future of option of company here. I could return an option of T here, but this would mean that my library returns an option of T, and in turn that my library requires the users to use cats as well. But I want the users of my library to only require Scala, pure Scala. So that's why this is a good practice to return the built-in Scala types here. In your private methods, feel free to manipulate the monad transformers, because they have some utility methods and it's nicer. But in the public methods, please return the built-in types. Also, here we have a single level of nesting. So we have a future inside an option inside the future here. If you wanted to have one more level of nesting, it would become complicated, and then monad transformers may not be the best solution here. Okay, I think that's all I had. The code will be available on GitHub, so I'm going to share the link on Slack as well. So thank you very much for your attention, and I'm happy to take questions if there are any.
Thank you, Jacek. This was a really illuminating talk. We have one question from Rahul Agrawal. He asked, what is your view on using future sequence?
What is my view on using future sequence? Well, I would say it depends, because to use future sequence, you need to understand the behavior. I would be happy to get some more details, so maybe you can.
Oh, sorry. There is a second part for this question. What is your view on using future sequence in terms of performance? We cannot hear you, Jacek.
Still, I'd like to have some clarifications on that, so I'd be happy to discuss it on the Zoom session where you can have some interactions, because here I think it could be difficult. So please join the Zoom session. I'll be happy to take this question then. Because I need some more details.
So then that would be it for this talk. Thank you very much, Jacek, and I would like to invite everyone for the Q&A session with Jacek on Zoom. You will find the link for it on Slack and on Hopin as well. Thank you.